Hello everyone. We are going to present our topic on face recognition system for low resolution images. Our team consists of three members: I Joshika, Samrathpreet, Singh, Randhawa and Sunny Chaturvedi. So let's first talk about the task definition. We are basically developing a DL model for facial recognition in low resolution images. This is formulated as a supervised learning task or classification problem where the number of classes is fixed. We can see in the image above like what exactly are we planning to do, that these two images belong to the same person. So basically we are recognizing the faces of the person. So the dataset used is CFPW, which we will be talking about later as well. This dataset used had good resolution images, so we needed to manually create low resolution images for our task. So let's also first talk about some of the previous studies on facial recognition. So first one is the deep face recognition, where high resolution images were used which predicted the class to get accuracy of 0.98. There also the same model directly over high resolution images was used, which is without converting them to low resolution, and finally the accuracy reached was nearly 0.99, hence replicating the results, but our problem definition involves face prediction for low resolution images. So we propose some ensemble multimodal architecture. Second one is VARG FaceNet, where in this architecture the accuracy was also 0.99, but again using high resolution images, but since we are targeting low resolution images. They used different blocks of convolutional networks in this, namely normal, downsampling, embedding and head setting, which we have gone through to develop our architecture. Third one is Deep ID3, where authors proposed joint identification verification supervisory signals which are added to the last fully connected layer as to better supervise early feature extraction processes, and also the accuracy obtained was nearly 0.99. Next slide. So again continuing with this, some image resolution based previous studies. First one is the SWIN IR, which was the 2021 state of the art. Here the authors basically proposed that an architecture involving CNN was used to develop high resolution images, and they used a block of several CNN layers and called it SWIN transformer block for this. Also, second one is the image super resolution using deep convolutional networks. Here this study proposes the use of convolutional networks for image resolution, and so we will also use CNN for the same. Next slide. So talking again about the data set which we are focusing on is CFPW, which is celebrities in frontal profile in the wild. So this is the data set where images of celebrities in frontal and side views are there, and there are 500 classes which each of them contain two directories, namely frontal view which has 10 images and profile view which has 4 images. We have only considered the frontal view for our model, that is 10 images for each class.
Okay, so this is the our proposed architecture. First of all, we will since we don't have the low resolution images. First of all, we will use pre-processing techniques to create the low resolution images, and also we will for each of the low resolution images we will have a high resolution image, and we will train a deep learning CNN for as our model 1 for conversion of low resolution image to high resolution according to our original problem. Then using another deep learning model which we named as model 2, we will identify the high resolution to its original classes. This is formulated as a supervised learning problem now, and if we combine both model 1 and model 2, the final pipeline will be consisting of input image which will be a low resolution image, and it will be mapped to the following its corresponding class. And here also we will first of all train model 1, then we will train model 2, and then once again after combining both the models we will again just hyper tune fine tune the combined model. So in the pre-processing, since we don't have the low resolution images, we first of all need to create it. For that what we have done is that there were images of various sizes were in the data set. So we loaded all of them in 50 by 50 size and then resized them into 224 to 294 using bicubic interpolation that is available in the OpenCV library, and made them considered these 224 into 24 images as low resolution images. The example can be seen here. This is a low resolution image which was interpolated after it taking input in 50 cross 50 and then interpolating it into 224 to 224. Then again, for the high resolution images of our model 1, we loaded all the images directly into 224 to 24 size, making it high resolution model. So the second image is of that kind. Uh, so as I discussed earlier, we will have two models and a combined model in comprising of both two. So model 1 will be a normal CNN, which will be trained on low resolution images obtained in the previous step, pre-processing step, previous step that is. And its output will be dataset images, and it is a supervised learning problem. For model 2, we have trained another CNN for classification of images. Here we have used the transfer learning of VGG phase. VGG phase we will discuss later in our slides. So it was a pre-trained neural network which was developed by the Oxford VGG group. So we fine-tune it according to our task, and then finally combining both the models using transfer learning from model 1 and model 2, we train our combined model for the final pipeline once again. From here, and now Samrit will go over the models which we have developed in detail. We will talk about the hyperparameters, and Samrit will continue from here.
Yeah, thanks, Singh.
Samrit, your screen is visible, and you can continue.
So I will mainly focus on the implementation part. So firstly, I will focus on the model 1 layer. So as we discussed that we have gone through swine IR and other state-of-the-art studies. So we will also propose a convolution 2D networks. So basically, we are having three layers of con 2D for this low resolution to high resolution conversion. So first layer has 64 filters of 9 cross 9 each. Second layer will be having 32 filters of 1 cross 1, and third layer has 3 filters of 5 cross 5. So as we can see on this right hand side image, we will be having an input image of 224 cross 224 cross 3, which is nothing but the interpolated low resolution image of 50 cross 50 to 224 224, and the output will be a high resolution image. Now this training of this model 1 will the we have used three images per class, total 1500 images for training this model 1, and we have also given some random 150 images as the validation images. We can see on the right hand side that as the box increases, the training loss and the validation loss both come to near zero for both the tasks. Now the hyperparameters and the input-output format for model 1, like images that we have used, that low resolution and high resolution will be containing the pixels, and pixels are usually ranging from 0 to 255, so we have to normalize this data. So we divide the whole array with 255 so that the whole data is between 0 and 1, and now the learning rate is initially set to 0.01, and we have used step decay as the number of epochs are increasing. And the optimizers we use for this is Adam optimizer, and we have used mean square error as the loss matrix. And now coming to the model 2, that is the VGG phase. This VGG phase is particularly a used model, or developed model by Oxford University Visual Geometry Group, and this model gives 98.78 accuracy over LFW dataset. And on the right hand side, we can see different types of similarity. So given an image, it will output some vector of that image, that what is the vector that this belongs to some class. So with or the matrix of cosine, Euclidean and Euclidean L-square distance, we can see the performance of this VGG phase. And the dataset that for which the VGG phase has been particularly trained is 2.6 million images for to tune this model weights. We will directly download the model weights of this and then fine tune these model weights on our dataset. So this is the basic architecture of VGG phase. It consists of convolution layers followed by some maxpool layer. So particularly this is considered as one block, and so there are particularly one, two, means five blocks, and after that there are some fully connected layers and followed by a softmax function, so that we can get the probability of an image belonging to each class. So similar to this, this is the model 2. This is our model 2 architecture. We have used from input layer to FC7, that is this layer, FC4096 second layer as it is, and upon that we have added our new dense layer, which is which consists of output of 500, and activation uses softmax again because we also need to predict the probabilities. Now the hyperparameters and the IO format for this model 2, similar, the same set of images that were used for the training of model 1 are used here for high resolution and passed, and the class output that we want to predict is passed as the output y, and here also images are passed by normalizing them. The output class is a number from 0 to 499. Yes, so we can't really pass them. We have to pass one hot encoded vector for them. As I said earlier, that we have added one layer over the SC7 layer of BGP FaceNet, and the learning rate here was 0.01, and again we used the step decay as the number of blocks increased, and the optimizer here we used was SGD. So basically we tried with different optimizers, but for like Adam and other optimizers, it was getting converged to a local minimum. So we use SGT with a momentum of 0.9 and setting stop value of 2. And so training with this value, it was giving very good results. And the loss was obviously categorical cross entropy as we are trying a classification model. Now, basically we have developed two models, model 1 and model 2, and now we have to develop this combined model. Now this, for this combined model, we have to fine tune the model weights for both of them, and for that we are using 4000 low resolution images. So as we develop low resolution images for our model 1, similarly we will develop 4000 again resolution images and pass this to this combined model, and the rest 1000 images we will be keeping them for testing. Now the optimizer here is again STD with momentum and losses categorical cross entropy. And between the model 1 and model 2, we have also like added two layers. One is the dropout layer and the other is the drill acquisition layer, so that overfitting doesn't happen, and the also the model doesn't get stuck over local minimum. Now coming out to the results, the accuracy score is 0. The overall accuracy score is 0.669, and we can see that we are giving very low resolution images, that is 50 cross 50, and converting them to 2 to 4 cross 2 to 4, and so that's why uh, we believe that the accuracy is quite low. But still, uh, also we can see that for each image only 8 image for each class only 8 images are giving as the input, and 2 images are used for testing. So as testing has only very less number of images, so even if one image gets mispredicted for each class, which obviously will happen, so that's why the accuracy score in our opinion is coming to be slow, to be low. So references used are, so various blogs we used and various papers that we discussed earlier in the previous study were used to develop this architecture. So like DFS architecture, what WADG, FaceNet, DeepID3, SwinIR, and other architectures were referenced for this. And so this was all from our side, and thank you.